SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering Module 3 Gas Turbines and Combined Power System. So, in this second lecture we are going to look at the Brayton cycles, and moreover in the first lecture we have discussed about the thermodynamic analysis of Brayton cycles and how Brayton cycles becomes the very vital thermodynamic cycles by which the gas turbines are being operated. And also it was emphasized in that lecture that we can extract the work output as well as thermal efficiency in a conventional Brayton cycle. But then what happens, certain modification needs to be required in the conventional Brayton cycles. These modifications are essentially or mainly due to the fact that many times we need to see or we need to maximize the power output, as well as we also expect that system or cycle should operate at its best possible efficiency. Also, due to irreversibilities, there are losses and they are also quantified in terms of efficiency of various components. Considering this, or an optimum Brayton cycle needs to have certain additional requirement. So, that is the reason we emphasize the non-ideal cycle. This non-ideal cycle is mainly associated whenever there is a friction, also when there is a losses in the steady flow components of the gas turbine units, and these are unavoidable. So, that is the reasons we need to analyze the non-ideal cycles. Now, the sources of non-idealness, that means a cycle needs to be operated through regeneration mode. There has to be intercooling which is required at the compressor end. We also need to expect that gases are expanded at much higher temperatures. So, that is the reason we require turbine reheat. Another way of improvement of cycle efficiency and work output is through water injections. So, when all these components are introduced, so ideal Brayton cycle becomes a complicated device, and for which we expect each component does not behave in an ideal manner. So, main objective of this lecture is to look into the necessary modifications that are done in the Brayton cycles with an viewpoint of improving or maximizing power output and efficiency. So, to start with, the Brayton cycle normally consists of two reversible isentropic processes and two constant pressure processes, as shown in this pressure, volume and temperature entropy diagrams. So, the cyclic processes that are process 1, 2, the gas is compressed in an isentropic manner, and process 2, 3 is constant pressure heat addition, process 3, 4 is isentropic expansion in the turbine, and process 4, 1 is heat rejection process. So, here in the compressor we give work input WC, and in the turbine we get the work output WT, and Q in also is added in the process 2, 3. Q out is heat rejected from process 4, 1. In the TS diagrams we also have isentropic compression 1 2, constant pressure heat addition 2 3, isentropic expansion in the turbine 3 4, and constant pressure heat rejection process 4 1. So, here we have net work output denoted by difference in the turbine work and compressor work, and heat addition that is taken place from the fuel in the combustion chamber, that is Q in, and Q out is heat rejected in an heat exchanger. So, this is what we have made in the last class, the entire thermodynamic analysis. Now, let us try to understand what is the non-idealness. So, the non-idealness is mainly associated with the fact that isentropic compression and expansion are relaxed in the compressors, so that we can introduce the term efficiency, which is called as polytropic efficiency or adiabatic efficiency or isentropic efficiency for turbines as well as compressors. We also introduce the pressure drop, which is accounted in during heat addition or heat rejection processes. In a typical non-ideal cycle or in a workable mode, what we expect is that isentropic efficiencies in the range of 85 to 90%, and whereas the other non-ideality due to friction that can happen in other components like heat exchanger, combustion chamber, gas inlet and outlet, regeneration and mechanical losses. Now, what is the effect of this non-idealness, for example, in the polytropic efficiency? So, at the process, if you look at the pressure volume or temperature entropy diagram, so had the process been isentropic, the compression would have been 1 2s, but due to this non-idealness, we are blending up giving higher work input. Similarly, for in the turbine process, if the process would have been isentropic, then it would have reached 3 to 4s, but due to non-idealness, it is reaching 4. So, this cycle which is shown as 1, 2s, 3, 4s and 1, it is an complete closed cycle, and it is a which does not account any kind of non-idealness, whereas actual cycle becomes 1, 2, 3, 4. So, our main intention is that by introducing these terms, we need to quantify the net work and cycle efficiency. So, to start the thermodynamic analysis, as I mentioned, due to by introducing the term turbine efficiency eta T and compression efficiency eta C, we can write down the net work output cycle, which is actually reduced by this term. Turbine work is reduced by with the term efficiency, so that is eta T into W T. Compressor work is also increased, so W dot C by eta C, that is compression efficiency. So, thereby net work output also is decreased. Even then also thermal efficiency we can, based on the calculation of W net and heat addition, we can actually calculate the net work, net heat, then we can calculate the heat added in the cycle. So, then net work can also be calculated. So, with all these numbers, we can actually find out what is the thermal efficiency of the cycles. Now, how do you define this polytropic efficiency of or isentropic efficiency for compressor and turbine? We mentioned that is nothing but the isentropic enthalpy drop to the actual drop, that is for compressor, but for turbine actual drop it is to the isentropic enthalpy drop. Since we write this gas as an ideal gas, we introduce H is equal to Cp times T, so that enthalpy becomes function of temperatures. Normally, when you deal similar kind of efficiencies for steam turbines and all, we used to get this value directly from the steam table, and but for since in this gas turbine cycle your working fluid is purely gas. So, ideal gas assumption we take, and accordingly enthalpy is represented in terms of Cp times T. So, compressor and turbine efficiencies are introduced in terms of temperature differences. So, after having analyzing all these things, what we can expect from a non-ideal cycle is that Both cycle efficiency and specific work strongly dependent on optimum compression ratio and maximum cycle temperature. So, in a typical gas turbine plant, which is normally a single shaft direct cycle open air combustions with 16 stage compression and 3 stage turbine, it can operate with a diesel fuel which can produce 35 megawatt of power with a cycle efficiency of 30%. So, this system can operate at 500 rpm with overall dimension of this. So, basically this particular numbers essentially says that what kind of range or power requirement that a gas turbine cycle can achieve. Now, when I specify all these numbers, we expect that our main intention is about what is the power that is derived from the cycle and what is the cycle efficiency. And to achieve this, we expect what is the maximum temperature that we are going to handle, and that again is seen at the turbine inlet point. So, with these three vital parameters, we are going to look at the relations among the specific power and pressure ratio and thermal efficiency and pressure ratio. And in this graph, what we have shown is that a simple cycle, which is a conventional ideal Brayton cycle, and a non-ideal cycle. So, we have also emphasized the working expressions for work, net work and cycle efficiency, and if you put some realistic number and try to calculate, we can plot them. So, trend of these plots are shown in this figure. What you see or what you observe is that with increase in the turbine inlet temperature, obviously your specific work output also goes out, and of course, cycle efficiency also goes out. So, we can keep on increasing the turbine and inlet temperatures, but again there is a limitations in terms of fuel, and also there is a limitation in terms of materials for the turbine blade which we are going to be implemented. So, with that restrictions, the upper limit normally doesn't go beyond 1500 degree Kelvin. So, the analysis was normally done at the three temperatures, typically 1200 to 1400, and we are trying to plot them. So, once that temperature is fixed, corresponding numbers are also gets fixed. For example, specific power, maximum specific power is also gets fixed. Also the cycle efficiency also gets fixed, but one interesting observation that you see here, that for an ideal cycles these curves are continuous and they are only dependent on the pressure ratio, but for non-ideal cycles various terms or efficiency terms comes into pictures. So, due to these reasons, the continuous or monotonous increase of the thermal efficiency or work output is not seen. Beyond some point or beyond certain pressure ratio, the non-idealness effect come into picture, and what we observe is that for at certain pressure ratio, non-ideal cycle efficiency suddenly drops, if you can see here. So, when this for non-ideal cycle efficiency suddenly drops, but one interesting is that with this you can see that the non-ideal cycles there is a sharp rise. For example, if you say 1400 degree Kelvin, the thermal efficiency shoots up immediately, retains it for a while and then drops, where at 2200 Kelvin it suddenly drops. That means there is no range of it suddenly drops down. So, because of these reasons, it is always advisable that we go for very high temperatures, and side by side we also look at corresponding specific power or work. So, this is one important observations. Second observation that I can say that although it rises sharply, the non-ideal cycles are not operated at a very high pressure ratio. That means, with increase in the pressure ratio, after one particular point the efficiency suddenly drops, also work output also suddenly drops. So, we need to find out for maximum work what is the optimum pressure ratio, and optimum pressure ratio shifts gets reduced when we are increasing the cycle temperature, and that is the reason the optimum value or optimum pressure ratio shifts towards the left. That means, at higher pressure ratio we cannot operate non-ideal cycles for a longer time, or in other words we need to find out what is the range of optimum pressure which the cycle needs to be operated for generating maximum work. So, this is the essential motive of these non-ideal cycles, and we also have to see that non-ideal cycles have a better approach in terms of improving the cycle efficiency and work output, but this non-idealness, first category of non-idealness we see in terms of regeneration. So, basically there are three modifications that are done for a conventional Brayton cycles. First is regeneration, second is compressor intercooling, third is turbine reheat, and fourth is water injections. Out of these four, we mainly concentrate on regeneration, compressor intercooling and turbine reheat to the most possible extent. And although there is some mechanism in which water injection is also used for improving the work output, and that is mainly done for aircraft engines. So, what does this mean by regenerations? So, regeneration in terms of steam cycle, it is viewed as it is the internal heat exchange within the cycle, but for Brayton cycle what we see is from this conventional or classical Brayton cycle is that turbine exhaust temperature is often higher than the compressor outlet temperatures. So, that means we have not utilized this efficiency of the fuel in a complete manner, for which the exhaust temperature is seems to be much higher than the compressor outlet temperatures. So, how effectively we can manage it? So, to do that, what we normally do, instead of releasing the turbine exhaust to the atmosphere, we use a regenerator. The purpose of this regenerator is that if you look at this particular cycle, there are two fluids, one is high pressure compressor, high pressure air enters to the regenerator, but that is not at very high temperature. But what we do is we are using this exhaust from the turbine, that means at state 4 the exhaust from the turbine is getting utilized. So, in this cycle we have these combustion products and in this cycle we have air. So, air is getting heated by the in a regenerator in which heat exchange takes place from the combustion products to the air. So, it is a kind of preheating of air before it enters to the reactor or combustion chamber. So, that way, in that way what we have shown is that instead of we are pushing this outlet temperature, that is 2, to somewhere by taking heat from these combustion products from 2 to 2 dash or 2 double dash, and also we are reducing the exhaust temperature which was supposed to be at T4, now it has now come back to T4 dash or T4 double dash. So, that way 0.4 shifts to the down, 0.2 shifts to the towards the up, and a particular balance is done by which heat exchange can be to some extent maximum possible. So, in this particular graph what we can see here, what is the maximum possible temperature change, and that is nothing but difference between T4 and T2, which is the difference between turbine exit temperature and the compressor outlet temperatures. So, that is the maximum possible temperature change, but the regenerator, the temperature due to this heat exchange, what is the best possible way that heat exchange takes place? We define the term what is called as effectiveness, which is nothing but T2 dash minus T2, which is the actual temperature rise to the maximum possible temperature rise. And that way we call this as a regenerator efficiency, and a typical gas turbine cycles we expect that regenerator should operate with 75% effectiveness. So, through that way we can see that by using this regenerator, if you look at correlate this temperature entropy diagrams with this thermal efficiency of the cycle, we can see that there are some locations at point A at a one particular temperature. For example, if you look at this particular graph, thermal efficiency versus pressure graph. So, initially your thermal efficiency shoots up and the efficiency becomes maximum at this point, and which means that we are expecting the maximum possible work from the turbine. And through this process, that means, and if you include a regenerator in this circuit, then possibility of heat exchange can take place at point A. So, where point A is nothing but the intersection point for a simple cycle and non-ideal cycles. So, beyond this point A, it is expected that the gas from the compressor outlet will be no longer heated, because we are crossing the maximum possible temperature rise. So, beyond point A, it is not possible to operate the regenerator. So, through this process, what extra advantage we get is that the pressure ratio for similar output, we can go for higher pressure ratio for operating the cycles. So, that is the extra advantage we get through this regeneration process. So, it has been emphasized here that when the efficiency curve of a regenerator cycle cross the simple cycle, the effect of regeneration on efficiency is negative. So, these points indicates the pressure ratio at which exhaust gas from the turbine are cooler than that of compression. So, the another effect is that although the regenerator has role in improving the cycle efficiency, but it is does not have much effect on the specific power. Hence, the regenerative cycles are more efficient than simple cycles, because there will be a reduction in the fuel consumptions by 30%. That means, when air is preheated, there is a reduction in the fuel consumption and it can go up to 30%. So, through regeneration we get improvement in the cycle efficiency without loss of any power, first achievement. Second achievement is that we can go for reduction in the fuel consumption. So, these 2 points are very vital, that why we go for a non-ideal cycles that can operate in regeneration mode. Now, another way of looking at, because regeneration does not improve the work output. So, what is the mechanism that work output can be increased? So, if you look at your expression, net work is the difference between the turbine work and compressor work. Now, for maximum or more net work output, there are two possibilities. So, either you increase turbine work or reduce the compressor work. So, through this process your W net can be increased. So, the first type of change that we are looking at, reduce the compressor work. To achieve this, we introduce the term what is called as intercooling. Now, how do you do that? So, for that, if you look at a conventional flow systems like a piston cylinder mechanism, the flow work can be expressed in terms of VdP. V stands as a compression, that means work is input, and looking at V is equal to mRT by P. So, we can rewrite this workflow system in this manner. So, one important point that you need to observe here, that work in the flow systems can be minimized if your temperature is also minimized. So, typically this is a constant quantity, that means if you do this compression at lower temperatures, it is possible that we can reduce the compression work. So, that is the essential requirement technologically we achieve through this intercooling processes. So, what we normally do? We do this kind of intercooling in stages, and that is the reason we look at this particular figure, that in this Brayton cycles which is integrated with intercooling. So, intercooling is normally done at compressor stage. So, instead of single stage compressions, we have introduced 3 stage compression A, B and C, and in between we have intercoolers. So, basically there are 2 intercoolers. Now, through this process, what changes that we made here is that instead of going for compression process from 1 to X, we are doing that compression process in stages like 1, 2, then bringing back 2 to again the initial temperature which is 1, that is 1 dash, then do this compression again 2 dash, then come back to 1 double dash. So, through this process we are doing these compressions at lower temperatures, and had this process, you can imagine this to be a infinite number of stages, which is not also possible in a realistic way, but here 3 stage, 4 stage are conventionally achieved. So, through this process we are actually reducing the compression work and the cycle approaches to an erection cycles. So, instead of like these are the 2 constant pressure line, let is P2 and P1. So, to reach P2, instead of going through increase in the temperatures, we are actually going in a constant temperature line to some to the best possible extent. So, the process tries to be more towards the isothermal process. So, that way we are getting much benefit. So, how much reduction that compression work we can achieve, this we can find out for each stage what is the enthalpy difference, and it can be noted that a single stage compression is always higher than the 3 stage compression if done at a lower temperature. Another important point to be emphasized that in between we have intercooler. So, of course, we are increasing the pressure, but not at the cost of temperature. So, an expression can be found out what is the pressure ratio per stage. So, if your overall pressure ratio is Rp, that means that much pressure ratio you want to achieve through this compression process, then Rps, that means pressure ratio per stage, is square root of Rp, that means Rp to the power Nc, 1 by Nc. So, that is the idea that we say pressure ratio how do you achieve per stage. So, that way what we achieve is this, that improvement in the cycle efficiency, increase the work and efficiency. The increased cyclic work is mainly the reduction of the compression work, because the operation is done at lower temperatures, and through this process of course heat addition is increased, but this increase in the cycle work offsets the heat addition, and that results in the improvement in the efficiency. So, this is the summary what we expect after the compression intercooling, and similar concept we can introduce in the turbine side, and we call this as a turbine reheat. So, turbine reheat is, as I mentioned, to improve the net work you need to reduce the compression work through intercooling, that we have seen, or we can also increase the turbine work. So, that means instead of coming from expansion in the turbine in a single stage from 3 to Y, so we come back in stages 3 to 4, then reheat 4 to 3 dash, again come back to 4 dash and keep on reheating to the 3 dash. So, this reheating process, that means we are coming back from higher pressure P2 to P1 through an isothermal manner through this reheating process, and reheating normally is done for the maximum temperature in the turbine. So, that is this particular things says that we have a 2 stage reheat. So, after first stage of expansion, again it is fed to the heat addition systems, reheated, again come back to for the second stage turbine. So, that way we can increase both work and efficiency. So, reheat is normally done to increase both work as well as efficiency. So, the achievement of these two, intercooling and reheating, is that when cooling and heating are done at constant temperature with rest of the cycle ideal in nature, it would represent an ideal erection cycle, and this erection cycle has efficiency same as that of Carnot cycle operating between the same temperature limits. So, that is the advantage of reheating and intercooling. And at the end of this thing, reheating and intercooling, what we expect at this thing is that if you include reheat and intercooling, number of stages, everything into picture, then the general expressions of non-idealness with all non-idealities, we can find out the specific power and heat additions, and these two expressions, through these expressions we can model it the fact that net work can be improved and cycle efficiency can be increased. But greater the number of reheat and intercooling stages, higher is the efficiency, but at the cost of capital investment and size of the plant. There is another method in which we can the non-idealness also comes into picture. Normally we introduce the term what we call as water injections, and this method is normally used for gas turbine cycle in aircraft engines, which is mainly intended for thrust generations. And just to quantify the fact that normally in the gas turbine blades are always exposed to very high temperature in a continuous manner. So, there is a thermal endurance, and to reduce this to some extent, the turbine materials has to be chosen, that is one aspect, but even if the material is also chosen, and while implementing we can use this concept of water injections to cool these turbine materials. So, thereby we can partially improve this network, as well as we can increase the life of the turbine blades. So, water injection is a method by which power output can be increased with marginal improvement in the cycle efficiency. So, the increased work of the cycle is mainly due to the optimum pressure ratio after the injection. Now, what does we do in this? The heat of vaporization reduces the compressor air temperatures, and this produces the similar effect as that of intercooling. So, for gas turbines cycles, it is more beneficial if water is injected between compressor and regenerator. So, this particular cycle says that through water injection how the regenerator cycle gets modified. Okay. So, this is all about the non-ideal cycles and their role in the power generation processes. So, with our this basic understanding, let me solve a numerical problems that completely highlights the non-idealness behavior for a gas turbine cycles, which involves reheat, intercooling and regeneration. So, there is a big problem statement which I can simplify is the fact that it is a two-stage compression process, single stage turbine process, and two-stage compression is achieved through intercooling. We also have the maximum cycle temperature is 900 and pressure ratio is given. We also include a combustion chamber in which fuel is injected with a calorific value and combustion efficiency. To introduce the non-idealness, we define the term isentropic efficiency for turbines and compressors. Also, we have regenerator which is introduced in the cycle, and this has efficiency of 0.75. I think that is a missing data, but it is a regenerator which is introduced here and which has certain efficiency. So, to solve this problem, first thing that we need to draw its thermal circuit. So, we say that we have a compressor C1 and that is second compressor C2. It is coupled with turbine which is a single stage, and after this compressor we have a regenerator or heat exchanger. That means, exhaust from the turbine is getting utilized in the heat exchanger, and this is nothing but our heat exchanger is nothing but our regenerator. So, air comes from the atmosphere, turbine exhaust goes out and side by side it produces power when it is coupled with generator. So, in between the first stage and second stage compressions there is an intercooler. So, this is what we say compressor, two stage, turbine, generator, and this is heat exchanger. And we have also here combustion chamber. where fuel is added. So, let me put the notations. State 1, and we have also an intercooler. The compressor outlet enters to the intercooler. So, I will say state I, and after intercooling is done, it enters same state, same pressure to the second stage compressions. So, we get compression. After the compression, it is your state 2, then we have state 3, state 4, then we have state 5, state 6, turbine outlet goes at state 7, and finally, exhaust goes to atmosphere at state 8. And the thermodynamic cycle in TS diagram should look like this. So, minimum temperature is T1, maximum temperature is T7. So, in between we have 3 pressure lines mainly. So, from state 1 to 2S, then actual process is 2, then from 3 to we have this 4S, but actual process is 4, then somewhere 5 will be somewhere here, because stage 5 is in the heat exchanger, and finally after this combustion chamber, this is 6. So, 6 to 7 is your expansion. So, okay, so this is T6 maximum temperature. Expansion and non-isentropic expansion would lead you 7S and 7, and somewhere we will have 8 and come back to the state 1. So, with these notations we have 2 stage intercooling and then single stage reheat. So, the data we have to go step by step. First we start with compressor. Data that is given, P1 is 1 bar, pressure ratio is 6. So, your P2 is 6 bar, T1 is 20 degree centigrade, and that is 293 Kelvin. So, we can find out what is intermediate pressure, that is square root of P1 P2, and this is 2.45 bar. Then first stage compression, we write T2S minus T1 by T2 minus T1, that is denoted by this compression efficiency eta C, and this number is 0.82. And we also have isentropic relations, T2S by T1 is equal to P2 or Pi by P1 to the power k minus 1 by k. So, here k is equal to 1.4 for air, and Cpu we can, for air we can write 1.005 kilojoule per kg Kelvin. So, from this number all these parameters are known, T1 is known, Pi is known, P1 is known. So, this will give you, first expression is T2S, that is 378.6 Kelvin. Once we know T2S, we can use this compression efficiency term to find what is T2. So, T2 turns out to be 397.4 Kelvin, and in similar manner we can also find out the second stage compression, that is T4S by T3 is equal to P2 by Pi to the power k minus 1 by k, and this is 6 by 2.45 to the power 0.4 by 1.4. So, this will give you T4S is equal to 378.5 Kelvin, and then T4S minus T T3 divided by T4 minus T3, that is again 0.82, that is compressor efficiency. So, T3 is nothing but T1, that is same inlet temperature, which is 293 Kelvin. So, this number will give you T4 is equal to 397.3 Kelvin. Then similar way we do this turbine analysis. So, peak temperature that we achieve in the turbine is T6. So, T6 by T7S is equal to P2 by P1 to the power k minus 1 by k. Here I need to emphasize, for turbines we use combustion products. Should say gaseous combustion products, and for which appropriate value of k would be 1.33. So, this is what the basic difference, that when you use this value in the expressions. And we also have from this data, T6 is 900 degree centigrades, then this is 1173 Kelvin. So, from this expression we get T7S is 752.2 Kelvin. Of course, your P2 by P1 pressure ratio is 6. Now, we have turbine efficiency, that is defined by T6 minus T7 divided by T6 minus T7S, 7S isentropic temperature drop, and this number is turbine efficiency is 92%. So, 0.92. So, from this we arrive at the number T7 785.8 Kelvin. Then we move on to regenerator. So, the data is missing, that regenerator efficiency epsilon is 0.7. So, when you say regenerator, then we have epsilon, that is nothing but T5 minus T4 actual pressure drop, maximum pressure drop T7 minus T4, and that number is 0.7. So, all the temperatures value are given. So, this will give you T5 value. T5 becomes 669.3 Kelvin. Then combustion chamber. So, combustion chamber we write this expression like, so fuel enters and we get this heat. So, that is m dot f into calorific value of the fuel into combustion efficiency, that is the heat input that comes from the fuel, and how it is getting utilized, like MA plus m dot A plus m dot F, that is that goes out into Cp into T6 minus T7. So, here these equations divide both sides by MF, then we arrive at the ratio. Okay. Calorific value as given 40800 kilojoule per kg. Combustion efficiency already data is given 95%. So, from this expression T6 and T7 is already known. So, T6 minus T5. So, from this expression we arrive at m dot A by m dot F is equal to 75.56, or per kg of air we express 1 by m dot F is 75.56 per kg air. Then turbine work. we write that W dot T per kg of air, that is equal to 1 plus m dot F by m dot A into Cpg into T6 minus T7. Here Cpg gaseous product, we say write it as 1.08 kilojoule per kg Kelvin. So, putting this number, we arrive at W dot T by m dot A is equal to 423.7 kilojoule per kg air. Compressor work, so we write W dot C by m dot A. So, it has two parts. So, here it is only air. So, we write Cp T2 minus T1, that is first stage compression, plus T4 minus T3 second stage compressions. So, here you take Cp as 1.005 kilojoule per kg, because compressor handles only air. So, putting this number, we write W dot C by m dot A is equal to 209.7 kilojoule per kg air. Then we get net work W dot N, which is W dot T minus W dot C. This number is divided by m dot A. So, this number is 214 kilojoule per kg air. But we all have all these things, but what is given in, we have to find in terms of this power delivered by the plant, specific fuel consumption and fuel consumption per hour. So, for that reason what data we have given is flow rate of air 210. So, this network we obtain it for per kg of air. So, what we know is m dot A is equal to 210 kg per second. Now, we can find out what is power output. That we can find out P is equal to W dot N, that is 214 into mass flow rate of air, that is per kg. So, you have to multiply mass flow rate, that is 210. Then we have to introduce mechanical and generator, each has efficiency 96%. We have to multiply 0.96 into 0.96, because there are two efficiency, mechanical and generator efficiency. So, this number is 40972 kilowatt or approximately 41 megawatt. Fuel consumption, per hour, that is nothing but that is equal to 210 into 3600, that is in an hour. What is air fuel ratio? 1 by 75.56. So, this is 10005.3 kg per hour. Then specific fuel consumption, we say it is SFC, that is nothing but mass of the fuel into power that is produced. So, that number is 1005.3 kg per hour divided by power that is produced is 40972. So, this is 0.245 kg per kilowatt hour, because this is kg per hour and the power is kilowatt. So, kg per kilowatt hour. Then cycle efficiency. The cycle efficiency eta is nothing but W net by Q in. So, W net is already calculated as 214, but what you do not know is Q dot in, that is calorific value into combustion efficiency divided by mass of fuel flow rate. So, it is 40800 into 0.95 divided by 75.56. So, Q in happens to be 513 kg per kg air. So, cycle efficiency turns out to be 214 divided by 513. This number is 0.417. So, approximately 42%. So, a non-ideal cycle, by introducing all these components, we have the efficiency turns out to be 42%. So, typically conventional gas turbine cycles or ideal cycle has efficiency in the range of 30 to 35%, but through these component introductions the efficiency was improved to 42%. So, this is how I emphasize the need of non-idealness in the gas turbine cycles by introducing the concept of regenerator, intercooling and turbine reheat. So, with this I conclude. Thank you for your attention.